All right, you're a co-host, so you can admit people too and record. Well, you have 9 here. Some people might be without power though. $11. $12. Anybody lose power last night?
Yeah,
Nothing?
my power went out.
We did.
Yeah. If you're in Montgomery, the university, Auburn University at Montgomery lost power too. That area got hit pretty bad.
Our fence was completely removed.
We didn't have any bad damage where I'm at, but a lot of branches and stuff are down. 16.
Okay.
Anybody, how about other people that aren't in the Auburn area? You're in Montgomery, right, Will?
Yes, sir.
How about people in the lower part of the state or around Huntsville? Anybody?
We lost power in Huntsville.
Who's speaking?
Ashland,
Ashley? What part of Huntsville are you in?
over towards on the Athens side, Madison.
My brother, I don't know if he lost power or not, but he said they were having wicked storms last night when I talked to him. And he lives, if you know where Hobbs Road is, it's off of.
Yep. Know exactly where that's at.
Yeah, he's about a half mile from Hobbs Road in 231. And apparently they got really pulverized by some bad weather. I don't know if it hailed there or not, but a lot of people got hurt. I mean, hurt bad by this. Were there any tornadoes in Huntsville?
To my knowledge, no.
Now, the western part of the state did see tornadoes. I don't know how bad the damage is. You got 17. Let's see here. $18. 19. Lydia, can you see that? The people up there? Can you take care of admitting the rest?
I'll try. Yes.
Try to admit somebody, the next person, see if you can do it. You're a co-host, so I think you can record and admit people, but I'm not sure.
I think I've admitted a few people. I'm pretty
Good.
sure.
Good. All right. So out of the President's Council meeting this morning, there's nothing new to report except the university. There's been some damage to buildings from the storm last night. I think there's some flooding, but I mean, nothing major, and there's no change in operations. Are you all taking, or is anybody taking summer courses here?
I'm taking online ones, but I'm not going to be in person.
There's nothing but online. All summer's all online. Even the last 5 weeks is probably going to be all online. They haven't said it officially, but it's more or less planned for summer and possibly even in the fall, at least for the first 5 or 6 weeks, to be all online until this thing's brought under control.
Not good.
Well, tell you, the question everybody's been asking in different ways is, what about football season? And the truth of the matter is, that's the last thing they're worried about is football. They got bigger things to worry about. But the athletic department's budget is heavily based on a revenue stream from football, so they're worried about it a lot. But I wouldn't bet on a football season this year. All right, how many we got? We got 20. Keep an eye out if other people come. Now, let me take first, any questions from people? General questions before I go and start. My plan today is works and problems. That's my goal.
I did have a question about the homework, problem 7.28.
All right, let me get my cast the screen. Come on. Give me 1 second. And And then hopefully this will work okay. And which problem was it again?
7.28.
Okay. All right. Oh, this is a good one. Actually, this is a perfect lead into what I want to talk about. So if you can, turn on your cameras. If you don't want to, you don't have to, but it makes my life easier, to some degree at least. Because then I know at least I can usually figure out who understands and who doesn't. And if there's a lot of people that don't understand, then I'll try to restate something. So what they end up doing is they have a function cosine. What it actually says is cosine of pi over 2n. And it's being fed into a system that has a difference equation, y of n, plus 8 x of n, oh, I'm sorry, y of n equals y of n. Hold on for 1 second. I'm going to put on some additional lighting. All right. And this is important what I'm about to show you. Y of n equals 8 x of n plus 3x of n minus 1 plus 4x of n minus 2. All right, that's the difference equation that establishes input-output. Now, the way you think about this, if you have an input that's at a steady state frequency, it can be a cosine of omega naught n plus a phase angle, or it can be a sine of omega naught n plus a phase angle. If this is your input and it's going into some system that has an h of z equals e to the j omega naught, then your output will always be this. And I'll just call the output y of n. Y of n will always be of the form of, let me put a magnitude here of a. It will be a, whatever the original magnitude is. Then it's going to be the magnitude of the transfer function evaluated at e to the j omega naught, whatever that frequency was. All right, then it will be either a sine or a cosine. So it'll be cosine of omega naught n. Then it will be plus the original phase angle, and then plus the phase angle associated with h of e to the j omega naught. Now, what I'm trying to tell you is this. You actually saw something very similar to this when we did Fourier series analysis, and we turned the exponential series into a cosine series. The output will always be a scale. It'll always be proportional to the magnitude of the input. Then it's multiplied by the magnitude of the transfer function. That's a relationship to output to input. Then it's times a cosine or sine, either one. If it's a cosine, it's a cosine here. If it's a sine here, it's a sine here, of omega naught n plus the original phase angle plus the phase angle associated with e to the j omega n. Now I can prove that to you, and I'll just state a few things. You all realize if you have a cosine or a sine, for instance, if you have a cosine of omega naught n, forget the phase angle for now. What's the transform of that? Isn't that pi times delta of omega plus omega naught plus delta of omega minus omega naught? Do y'all remember that, class? I'm going to remember. This, I see some head shaking. Got 1, 2. All right, this is important. What does this delta function tell you? It says that that exists only at one frequency, right? Actually at 2, only at plus or minus omega naught, correct, class?
Mm-hmm.
Now, if that's the case, since this is a delta function, I'm going to just sketch this here, try to explain my rationale for this. If I look at the frequency domain right here, and this is omega, and I take a look at this, I know I have 2 delta functions, one at omega naught and the other at minus omega naught. And this is in the omega domain, right? And remember, if I put an input into the system, usually I think about really I could convolve it with h of n, right? Or I could multiply, I could take this and take the transform. This is the transform of the cosine right here. And I could multiply it by the transfer function, the value of the transfer function to get the output, correct? You follow me? If you have an input signal and an h of n, you could convolve these two to get y of n. Do you agree with me? Everybody?
Yes.
Right? If you have x of n convolved with h of n, you would get y of n. Or you could take the z transform of this, or the DTFT, the z transform, and you let z equals e to the j omega and not is the DTFT. You could take that and multiply it by the value of h, the transfer function evaluated at that frequency. Do you follow me? The frequency would be the coefficient there of n inside the cosine argument. Do you see that? Now, what does that mean? Well, if I take this and multiply it, the transfer function may look like this. Just suppose it looks like this. Well, then you would take the value of the transfer function there, multiply it by that pi times the delta function, and then you would take it back into the other domain. And effectively, the only thing you're doing is scaling the magnitude by h of omega naught. Do you see that? When you take these two and multiply them together, effectively what you end up with is pi times the magnitude of h of e to the j omega naught. And you still have delta of omega plus omega naught plus delta of omega minus omega naught. Now, there's one thing I didn't say, though. Not only does this thing multiply the magnitude, but there's also a phase associated with the transfer function. And the phase would be absorbed in the angle. So this would be the magnitude. And by the way, this is in the actual omega domain. And the phase would be added to it, plus the phase of really the original phase, plus the phase of the transfer function, plus whatever the original phase is. And then when you take that and go back to the other domain, well, the minute you see a delta function of plus or minus omega naught, you know you have a cosine. And the only thing that happens to that cosine, it's multiplied by the amplitude of the transfer function, and the phase of the transfer function is added in. So your output will look like this. And you can do this for any problem. You can literally take the cosine is equal to pi, right? I mean, you can, this is the transform of the cosine, right? You can take that and multiply it by the transform of h of z, whatever it is, evaluated at omega naught, plus or minus omega naught, and then take it back. You can do this as an exercise and show, in fact, this is what you'll get. Now, my real point is this. Anytime you want the output, if for a system that's a linear time invariant system, and the input is at a steady frequency, and how do you know it's at a steady frequency? Both sine and cosine of omega naught n are periodic, right? And that frequency is, if you think about, if that's the frequency omega naught, well, omega naught is what? 2 pi over t over the period, correct? You can calculate the period, but if it's periodic, it's called an everlasting signal. It's been on forever and it's going to stay on forever. Your output will always be at that frequency. And I'll rewrite this again so it'll be clear to you. Your output will always be of the form y of n will always be the magnitude of the function incoming. Then it'll be magnitude of the transfer function evaluated at omega naught. Then it will be cosine of omega naught times n plus the original phase angle plus the phase angle of the transfer function at omega naught. And that's the way it'll always be. Now, specifically about that problem. Let me just do that. The specific problem was they've got, this is an input and they want to compute the frequency response. Oh, well, this is the output, the y of n, but the frequency response is pretty straightforward. So here, if I take h of, and they want to know what the actual transform for the frequency response is, e to the j omega naught. And here's how you do that. When you see this equation, let me get another sheet of paper to do this. I'll try to be clear about this one. When you see this difference equation, y of n equals to 8x of n plus 3x of n minus 1 plus 4x of n minus 2. You can do it this way. First, do the z transform. It's the easiest. The z transform of this is what? Y of z equals, and then you can put x of z out here. Well, the z transform of x of n is just x of z, right? And then there would be a coefficient of 8. Does everybody see what I'm doing? Y of n would go to y of z. 8 was just a scale factor, and x of n would have a transform of x of z. Correct, class? All right. This would have a coefficient of 3, but it would be divided by z, correct? It's assuming no initial conditions. Does everybody see that? Let me spread you guys out a little so I can see you.
Move it down just a little bit.
Yeah,
Thanks.
sure. Let me. I'm not seeing a whole lot of you, but that's all right. You can tell me if something's up. All right, now what's the next one going to be? Plus what? 4 over?
Z squared.
Right. Now, if you look at this, that means the transfer function h of z is y of z over x of z, right? By definition, correct, class? That's simply going to be 8 plus 3 z to the minus 1 plus 4 z to the minus 2. So that's the z transform. Now, if you want the frequency response, the only thing you have to do is let z go to e to the j omega. Because now the radial, the factor, the coefficient in front of their rho is 1 for frequency domain response. You're at a radial distance of 1 in a z plane, and you're just going to go from 0 to 2 pi to get it. So h of e to the j omega here would be equal to 8 plus 3, and this would be e to the minus j omega plus 4 e to the minus j2 omega. And that's literally, that's correct. However, if you want to be clever, you can turn this into a couple of cosines, I think, fairly easily. You could do a lot of things. I don't even know what they do in the solutions on this one. That is the frequency domain. That's the frequency response. But then they want to evaluate the output for that constant input. So this is the correct frequency response. We could get clever and make it into a cosine. Yes and no. I could say this 3 is really equal to, what I try to get is a coefficient of 8 here, so I'd have to play with this, and a coefficient of 4 there, and it'd be a little too much trouble. This is fine. Do you all see that? Everybody? That is your h of omega. Now, getting back to the input-output relationships, if y of n is equal to cosine of pi over 2n, and there was no phase angle in that, right?
No phase angle.
Let me sharpen this thing. All right, no phase angle. Now this is x of n, my bad. X of n, y of n would be equal to simply, the magnitude of the input was 1, right? The coefficient of the cosine,
Yes.
right? So then we have to get the magnitude of this. Well, it's at this frequency, right? At pi over 2. So the magnitude of the filter, or h, right here, would be equal to h of e to the j pi over 2 would be equal to 8 plus 3 e to the minus j pi over 2 plus 4 e to the minus j pi. Correct, class? That's the j pi there, because there's a 2 omega, and omega is pi over 2. Does everybody see that?
Okay.
All right. Now, what is that going to be? Well, that would be h of e to the j pi over 2 would be equal to 8, right? And 3e to the minus j pi over 2 is minus j3, correct? All right? Minus j pi over 2 is minus j. And then this one, what is this? That would be minus 4, right? Because e to the minus j pi or e to the plus j pi is really e to the j 180 or minus 180 degrees. That's minus 1. Minus 1 times 4 is minus 4. Or really, this is 4 minus j3. Do you agree with that for h, your transfer function at pi over 2? All right, now what is that in terms of a magnitude? Well, the magnitude of h of pi over 2 would be 5, wouldn't it? 4 squared plus 3 squared square root is 5. Do you agree? Y'all with me? This is a 3, 4, 5 triangle. What about the phase angle of h of pi over 2? That would be what? Tan to the minus 1 with a minus side of what? 3 over 4, correct? Right? And that's minus 37 degrees.
Could you go over the phase angle again?
Yeah, my dog is mad because there's somebody in our backyard spraying it. Sure. When I take a look at this, 4 minus j3, right?
Oh,
4
it's the
would be
phase
out here, right?
Okay.
And then minus 3 is here, right? So we need this phase angle, and that would be the opposite, which is 3 over the adjacent 4, only be negative. Agreed?
Okay, that makes sense.
Whoever. All right, so that's the phase angle. Give me 1 second. Harper, you're not going out there. No. Quiet. We have some guy that comes by and sprays our yard, and our dog is, my dog is just a little excited. All right, now the output therefore would be, for this would be y of n equals magnitude of the input, which is 1, times magnitude of the transfer function, which is 5. Then it would be cosine of the original frequency pi over 2n plus the original phase angle, which was 0 degrees, minus 37 degrees. And by the way, circle that. That should be in radians. Put radians, right? That actually, in a calculation, you have radians here and degrees here. That is disallowed. So this should be changed to radians. Everybody okay with that?
Mhm.
Everybody? And does everybody have power here? Does anybody not have power?
I just got power back.
Are you in
like-
Auburn?
Yeah, I'm in Auburn.
I wonder how many people do we have here? Can you see any?
20 students.
There may be several of us without power that are unable to see this. And you are recording, Lydia? Okay, good. Now, is there any other question about this? That's it. That's how you do this one. In a nutshell, I want to make sure we're familiar with input-output relationships for steady state frequencies. Anytime you have a cosine or a sine or just e to the j omega naught n as an input, your output will be at that frequency, and the magnitude of the output will be multiplied by the magnitude of the transfer function, and the phase would be augmented by the phase of the transfer function. Everybody okay with that?
Dr. Baginski, this may be a really easy question, but when you did h of e to the j pi over 2, how did you transform e to the negative j pi over 2 into negative j? Is it?
Yeah, here, I want to show everybody this because this kind of question comes up all the time. When I have an axis where I have, this is the imaginary axis and this is the real axis. If you have something where you have a real value, call it A here, and an imaginary B here, then the relationship to this angle, the tangent of that phi would be equal to B over A. It's opposite over adjacent.
Yes.
That means theta would be tan minus 1 of B over A. Simply a ratio of the imaginary to the real part.
Yes.
If it's down here, if it's negative, all right, if B is now negative here, then this would be minus tangent of minus 1 of B over A. So I was left with this as the value, 4 minus J3, right? Hope you can see it, right? All right,
I was
that's,
just wondering how you got from e to the negative j pi over 2 to
oh,
negative
well,
j. That was
e to the j pi over 2 really is what? That's something, really what I should do is this. If I have e to the j theta, what does that actually mean? It means I have a vector of length 1 at an angle theta.
okay.
Y'all remember this from circuits? Right? It's always, think of this, it's this, I mean, how do I know that? Well, what is e to the j theta in terms of Euler's identity? That's equal to cosine theta plus j sine theta, right?
Yes.
All right, well, if you take the cosine of this, that's the projection on the real axis. The sine of that is the projection on the imaginary axis.
Okay.
But this really is, think of it the hands of a clock. It's got a magnitude of 1, and it's just wound by an angle theta in the counterclockwise direction. And if it's going this way, it'll be negative theta. So when I had e to the j pi over 2, that's this, right? Isn't that just j?
Could you move the paper up a little bit? Sorry.
Yeah, sorry. If I have e to the j pi over 2, that's just 1 at an angle of 90 degrees or at pi over 2 radians, and that's j. You're right on the j axis.
Oh.
And if it was minus j, then it would be here. It would be minus j.
Negative minus j. Okay. That makes sense.
And if it would be, if this was e to the j pi, now you take this and wind it all the way over here, so it's minus 1.
Okay. All right. That makes sense.
Okay.
Thank you.
Okay? All right. Next. I mean, if anybody's got any questions, actually these questions, this is the best way to do it. Let you guys take a look at stuff, and then if you don't understand something, I can take time to try to explain it. How about anything else? Ruth, do you have anything for this session right here? Nothing? Jack? Oh, admit somebody else is back in. What now?
Could we just do 7.29 just to make sure that
Yeah, we're gonna go. I'm gonna go through those. Is there somebody else in the waiting room? Can you
No.
check? Okay. 729.
Yeah, that was me. I just joined. I just got power back about 5 minutes ago.
Okay. Now these do not correspond with the numbers in our book. I want you to know that. They're problems in our book, but they're not the same numbers, and I don't know what happened. I think this might be a different edition. So 729 here that I posted was, now we've got 2 different frequencies going in. We have an input, hold on for a second. Thank you. How long do I have to, sir? Sir? I had a delivery and a bill from somebody. Sorry. Back to this thing. We have two frequencies here. If you look, cosine.
Can you move it down a little bit, please?
Yes. Yes.
Also, what question number is this?
29.
Okay.
But it's not 29 in your book. It's 29 the problems. So it's cosine of pi over 2 n plus cosine of pi n. Now here we have two different frequencies. You all see that?
Mhm.
And then they have a difference equation. And the difference equation is y of n equals x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3. It's really an average of the last four values, or four values. It's called a running average or a moving average, and it's called an autoregressive moving average. And if you take a look at this, right here, this equation, now we're going to go ahead and just get the frequency transform of that. So now I have y of, and I'm just going to call it of omega, all right? I could do the z transform first. Do you agree with that? And if I did the z, maybe you want to do the z transform first. So I could say y of z equals x of z. And then I would leave, I'm taking z out, x of z out of each one of these. The coefficient of the first part is 1, right? What's the coefficient of the next one?
Z to the minus 1.
How about, yeah, we'll leave it as z to the minus 1. I'm going to do z first, okay? Right? What about the next one?
Z to the minus 2.
And
Z to the minus 3.
that's right. Then you would say h of z is equal to y of z over x of z. Or it's simply 1 minus z to the minus 1, plus z to the minus 1 plus z to the minus 2 plus z to the minus 3, right? And what's next?
Do you plug in e to the minus or e to the j omega for z?
You let z be equal to e to the j omega, and that means my h of omega would be equal to simply 1 plus e to the minus j omega plus e to the minus j 2 omega plus e to the minus j 3 omega, and that's perfectly acceptable. That is correct. That is the right answer. All right. Now, once we have this, that's the filter. We could mess around with this, and I don't know how much he does in here, but we could actually, I don't know if he turns it into a trig function.
He doesn't do anything with it.
Good. Now, though, we have two different input frequencies, right? We have pi over 2, and we have pi, right?
Mhm.
Now, remember, this is a linear time invariant filter. So if you have one signal going in, you can get one output. And then a second signal going in would give a second output, and you can add those two outputs together to get the total response. Do you follow me, everyone?
Yep.
All right. What happens next? Well, go ahead.
You just plug in the different frequencies. And since it's like one of the properties is you can add them afterwards. So
Right, superposition. We're just going to evaluate them first. So this one, what is this one, people? It would be equal to 1. Pi e to the minus j pi over 2 is?
J.
Minus J.
Minus j, because it's minus, right? Minus j. How about the next one? E to the minus j pi. What is that?
Minus 1.
-1.
Right. And what's the last one? E to the minus j 3/2 pi.
plus j.
It's plus j. just think of that. You're winding it backwards, right? So if you think about the clock, that's e to the j0. This would be e to the minus j pi over 2 or minus j. Wind it one more time, e to the minus j pi, right? And then one more time, e to the minus j 3 pi would be straight up would be j. All right. And what is this?
0.
0, which is nice. That means that has no output, no part in the output. It's just 0. So what is h of pi? Go back to the original function. It would be 1. Keep going. What about this one?
Minus
Minus
1
1.
Right. What about this one?
plus 1.
1. What about this one?
-1.
Minus 1.
Minus.
Yeah. And that's 0 too. Is that right?
Yes.
Yeah, that's the
What in the world is this problem about? There's no transfer function. The output's 0. Okay. Well, I'm not sure why the guy did that, but I'll tell you one thing about this. You see how this is averaging 4 values? Look at, where's my difference equation? Right here. It's averaging 4 values. Now, the frequency of pi over 2 or pi, think about this. If it's the cosine of 0, cosine of pi over 2, cosine of pi, cosine of 3/2 pi, you're really averaging the value around a cosine waveform of 1 period. That's 0, always.
Mhm.
And it would be the same if you've got 2 pi or pi, which is not exactly helpful if you're trying to actually see something on the output that's meaningful. But that's the answer. We might as well do a few more because these particular problems, usually you don't know what to ask about until you try them. And I have a feeling some people have it. We'll go to the first one, 25. So the first problem, which is a very good problem, and I'm pulling it up here. And I'll just put it here and then talk about it. So for the first problem, I have, this is 29. Problem 29. It has h, they give you an h of z, which is nice, of z over, did we do this one, anyone? Or not? Okay. All right, now the first thing is, whenever you're doing an analysis of a filter in the z domain or in the s domain, you look at the poles and the zeros. So the zeros are pretty obvious, right? That's what value of z makes this 0, and there's only one, it's what? Z equals
0,
and poles are
1 and 2.
1 and 2, right? Real quick, as soon as you get the poles, you ask yourself, is it stable or not? And this tells me something. Is it stable?
No.
No, it's unstable. It's an unstable filter, which is important to know. It means the impulse response of this system will go to infinity, in a nutshell, okay? And all right, now, the next thing it asks for is the difference equation. Now, I've given you the solutions, but it's good not to look at them and just think through this yourself. To get a difference equation, what I really need is y of z over x of z, right? That's equal to my h of z, and that's equal to z, and now you have to multiply out the denominator. So you get z squared, right? And then you get minus 3z, and then you get plus 2, correct? Everybody? You all see it? Ashlyn, can you see this okay?
Yes, sir.
I'm just trying to get an idea. There's a thumb. If anybody has problems, just if you don't have a microphone on, just do something in the chat. But let me know, because I'm going to try to help everybody see this stuff. When I have this, now I multiply everything. First I multiply by x of z, both sides. And then I multiply by this denominator on both sides. So I have y of z times z squared minus 3z plus 2 is equal to z times x of z. Correct? What do I do next? And some of you don't have to do this step, but I recommend you do. Anybody?
Divide out the z.
Divided by C.
Z squared, right? Highest power.
Oh, yeah, yeah.
So this would be y of z, 1 minus 3 over z plus 2 over z squared equal to x of z over z, right? Everybody?
Mm-hmm.
Mm-hmm.
Next, what happens? We want the difference equation. People? Y of z goes to y of n, right?
Mm-hmm.
Minus 3 times y of
N minus
N
one.
minus
right, right. And then what? Plus 2 times y of
N minus 2.
N minus 2.
right equal x of
N minus 1.
1.
that's the difference equation. Now you can take these terms right here to the other side if you want, but it's not necessary. That is the difference equation. I don't know what he did, but I'll tell you. Take a look at it. Yeah, he just left it like I did.
Yep.
So that's the difference equation. Next, he wants what? He wants what does he want next? He wants the response to the input 2 minus 6, 4, right?
Yes.
And what he does is this. He gives you an input and he said, let x be equal to, and this is going to be just numbers with one underscore indicating where this n equals 0 is. It's 2 and then minus 6 and then 4. And this is the underscore. That means n equals 0. Well, I have this in the z, I have the z transform of this right here. I have it both here and I have here. So one way to do it, doesn't have to be this way, but probably the easiest way is just take x of z here. So x of z, do it the direct way. Remember the z transform is the summation of x of n times z to the minus n for n equals 0 to infinity. I just put the definition of the z transform down, okay? Now just run the math on this. Well, at n equals 0, it's 2, so it would be 2 plus minus 6, right? And then it's to the z minus 1, and then it's plus 4 over z squared. That is the z transform, correct? Everybody? All right, if that's the z transform, I can write this as 2.
Can you move it up, please?
Yeah. I can write this as 2z squared minus 6z plus 4 all over z squared. Do you agree?
Mm-hmm.
All right. Now, if I take this times h of z, and I'll write down, when I take x of z times h of z, this is x of z, so it's going to be, I'm going to factor the 2 out in front. And I get z squared minus 3z plus 2 over z squared. That's my x of z times h of z. And h of z was equal to z over z squared minus 3z plus 2. So this is h of z, and this is x of z. Do y'all agree with that?
Yep.
And what do you see happening?
A lot of cancellations.
Yeah, a lot of cancellation there.
That goes, right? and I have 2 over z, right?
Mhm.
Well, what's the inverse of 2 over z if that's y of z? Y of n would be what? Think about it. If you have delta of n, that goes to 1, right?
Mhm.
2 of
Delta
u then.
n minus 1 goes to 1 over z, right?
So it's 2 times delta n minus 1.
That's right. So you know y of n is just 2 times delta of n minus 1. And he has that, I'm sure. Agree?
Mhm.
Then he wants the response to 1 minus 1. Well, I'll tell you, this one, you can just use the difference equation if you want, but you can go ahead and get the z transform to that. So if I have x of n equal to 1 minus 1, and the zero's there, then you could say x of z is equal to what? 1 minus 1 over z, correct? Or it could be z minus 1 over z. You agree with that?
Mhm.
And then you could say that y of z would be equal to x of z, z minus 1 over z, times h of z. And h of z was what? Z over z minus 1, z minus 2. I'm using the original form now. Do you agree with that?
Yes.
Mhm.
Catch up with me if you're behind. Just look at the original problem statement where you had h of z is z over z minus 1, z minus 2. Agreed?
Mhm.
Yes.
And you see this goes, right?
There was 1 over z minus 2.
Mm-hmm. And I have 1 over z minus 2. What do I do with that? Anyone?
Is that it looks like it should be a n to the u of n, but it's missing a z, so it's a to the n minus 1, u to the n minus 1, and n would be 2. A would be 2.
AA would be 2, yeah.
I'm going to do it this way, just for everybody. So first, delta of n. I do this a lot when I'm dealing with z transforms. Goes to 1, right? Delta of n minus 1 goes to 1 over z. Delta of n minus 2 goes to 1 over z squared, and so forth, right? When I have this, I didn't hear some of the responses. What did you say?
I think he's correct.
So it's like we know that a to the n times u of n is z over z minus a, and but because it's missing that z in the numerator, we know that it's the n. Everywhere there's an n, there's an n minus 1.
Right, a to the n, u of n. You're ahead of me. That's right. From here, I know that's z over z minus a, right?
Mm-hmm.
And I also know if this is like an x of n, then x of n minus 1 would be a to the n minus 1, u of n minus 1. And that would go to 1 over z times z over z minus a, or it would be equal to 1 over z minus a, correct? Everybody? I didn't need to do this. I usually do this over and over again and run through these and then just keep on writing them because it seems to help. Here, I know that a is really equal to 2, right? And that means my output is actually y of n here is equal to 2 to the n minus 1 times u of n minus 1. Agree? Sometimes people don't make the mental connection real quick between this right there and this form of z over z minus a delayed by 1, the n domain. Okay, everyone? Let's do one more and we'll go. I know I'm just about, I got, on my computer, I got 1 minute left. I don't know if that's true or not. But
That seems true.
I'm trying my best to get through this. So next is okay, let's talk through problem 30. And here, and I'm going to make a comment. I'm going to ask 2 questions about this to see how everybody does. Everybody can see problem 30 on the screen, right?
Mhm.
All right, it's just an input of 1, which is DC, plus 2 cosine of pi over 2n, plus 3 cosine of pi n. There's your difference equation, input and output. And this is called an ARMA filter. It's an autoregressive moving average filter. It just means the average moves in time over the points taken, but it's always going to take x of n, take the point before there and multiply by 4 times x of n minus 1, plus 3 times x of n minus 3, whatever the value of n, to get a new value of y. So it's taking the last, this case, 3 values. No, it's actually the value at n, n minus 1, and n minus 3. It's omitting n minus 2. But it's called an autoregressive moving average filter. Compute the frequency response. Is everybody pretty confident they can do that?
Yes.
You can just see this, right? It's going to be what? 1 plus 4e to the minus j omega plus 3e to the minus j 3 omega. But pretty much, right? You can look at that and get that. So we got that. Now y of n. Well, these are at constant frequencies. The 1 is at DC, right? So if this is the frequency response, omega is 0 at DC for the 1. Do you agree? At DC, though, so let's take a look what this is. So 1 plus 4 plus 3, that would be 8. Agree with? Because e to the j0, omega b0 is 0, correct? So the DC part for the output, you're going to have it for the 1 would cause an 8. Now, then you would have 2 times the magnitude of this transfer function of pi over 2. What's that going to be? It's 1 plus 4, right? It's really 1 minus j4, correct?
Yes.
And then it's going to be plus j3, right? So it's 1 minus j4 plus j3, or 1 minus j, right? And that's a magnitude of square root of 2, and it's a phase angle of minus 45 degrees, or minus pi over 4. Agreed? 1 minus j has the magnitude of square root of 2, correct, class? All right, and I don't know what he has here. Yeah, here it is. Magnitude of square root of 2, it's at an angle of minus 45 degrees, or minus j pi over 4. And then you need the filter evaluated at pi. So then you do the same thing using this for pi. And at pi, it's 6e to the j pi. And we could do it, but when it's pi, it's what? 1 minus 4, right? When it's pi. And then what happens here? It's going to be that's right. And you end up with minus 6. And minus 6 is 6 at e to the j pi. And that can be plus or minus pi, j pi. So your response is just the original magnitude of DC times the h, the magnitude of h, which is h, plus the magnitude of the filter, which is square root of 2, times the original magnitude 2, times the cosine of pi over 2n, minus pi over 4, because the original phase angle was 0. But if there was an original phase angle that was non-zero, it would be added, plus the original magnitude of the third term, which is, what was it, 3 cosine. So it'd be 3 times 6, that's the filter magnitude, plus cosine of pi n, plus the pi's there has to do with the filter's phase. You all see this, class? I wanted to go through these because usually going through them answers questions that you haven't thought of. Everybody good with this? Any last questions or any comments for the good of the group? Anybody? Nothing?
I had a quick question, I guess, like, did you have any announcements for like homework or anything like that at the beginning? Like, I came in late. We just got our power back about 20-25 minutes ago.
The only thing I'm doing is I gave you a set of homework with solutions. I wanted you to go through it, and then I'd answer any questions you have. Turn on your mic, Ashley. I can't hear you. Turn it on.
I'm sorry, sir. I was speaking to somebody else in the room.
Oh, that's all right. Go ahead. I thought you were trying to tell me something. If you guys have any questions, I'm not seeing any.
Will
How's
they
it-
have homework assigned this week?
Yeah, I'm going to put some up today.
Okay. When
I'm
will
gonna-
it be due?
Well, if
Just do it.
if it's a collected one, I'll give you it should be done by the next class period. If I'm going to get one or take one up in Canvas, I may do that this week. I'm actually thinking about a quiz on Friday, just where everybody turns on their cameras, but I'm not sure. I'm going to give you some homework. I'm going to give you some homework that I'm asking everybody to do by the next class period, so everybody's up to speed. And then I may ask for one problem turned in that's going to be a little more difficult and not with a solution. Okay.
Okay.
Let me think about that though, how to do this best. And how many participants do we have?
15 right now.
Oh, a lot of people jumped off. Okay. All right. Well, have a great day. If there's further questions, I'll hang out for a second. You got anything? Anybody? Nope. Well, have a great day. And give me any feedback on the lectures, anything I can do to make it better.
Okay.
All right. Go ahead.
All right. Thank you.
Thank you.
Did you have a question or not? Or statement?
No, I was just wondering how your dog was doing.
My dog is surviving this crisis. She can't go out in the backyard because they sprayed, and she's a little mad about that. But I'll take her for a walk. She'll survive. It'll be tough, but she'll survive. She'll survive. All right.
Thank you.
All right. Have a great day.
You too.
Take care. Bye-bye.
See.
All right. And Lydia, if anybody has any problems, let me know. All right. Because you're still on, and I don't think anybody else is. But yeah, if anybody's got problems on that GroupMe or needs some extra help or whatever, just let me know.
Yeah, some of the quiz solutions aren't put up still. I think it was from like the earlier chapters. I think I sent you an email about it a long time ago, like before spring break.
Which ones?
I don't exactly remember, but a few of them didn't have solutions posted on the OneNote.
I think we did them in class, but I'm positive we did all of them in class. But I mean, just if you want some specific solutions, send me it again, and I'll get them up.
Okay.
All right.
Well, thank you.
But if you have suggestions, I'm open to anything, how to change the class for the better. Anyway, you too. Bye-bye.